comments or corrections. What I will say here has already been covered, but maybe I'll just at some places I'll reword things or slightly change perspective. That's all. Okay, so well, let's talk about toric surfaces in some more computational detail, because much of the story much of the examples are related to those. So let T be a two-dimensional complex torus. So what's a toric surface? You want either a full or partial compactification of T, so T should live densely in X, and the action of T on itself by multiplication should extend to an action on X. Now, there are two important lattices associated to T. One is the character lattice, the homomorphisms from T to C star, which is abstractly isomorphic to Z2. And by M sub R, it's just tensoring with R, you get R2. And N is the lattice of one parameter subgroups, or the co-character lattice. So it's homomorphisms from C star to T. It's the other way around. It's dual to M in a natural way. So in order to describe a toric surface combinatorially, one chooses so-called a fan in N sub R. So what is a fan? It's a collection of rational polyhedral strongly convex cones, and the sets should be closed under taking faces of cones. So faces of cones should again belong to big sigma, and it should be closed under taking intersections. Strongly convex is it doesn't contain any positive dimensional linear subspace, so it makes an acute angle at zero pictorially. Rational is generated, I mean, the boundaries are generated by rational vectors. Yeah. Now, for each cone in the fan, you associate an open set, namely U sub sigma, which is the spectrum of the dual of sigma intersect M, which means you look at the lattice points, but remember those lattice points are actually characters. So they form some kind of algebra. So it makes sense to look at a spectrum, or otherwise you could view it as a group algebra. So and the point of a fan is because of the containments of faces of cones inside cones, this tells you a natural way to glue together these U sigmas. So that comes automatically with the information of a fan. And altogether, this gives you the toric surface. And each toric surface X does have such a description if you start from this abstract definition, like, you know, T acting on T, such that I guess you would have to also assume normality, but apart from that, it would have a fan description. Now let's see this on some concrete examples. So here, there are 4 one-dimensional rays. So sigma 1, 2, 3, and 4. And next to them, I wrote the primitive vectors along those rays. So vectors such that, you know, they are not positive integer, non-trivial positive integer multiples of any other integer vector on that ray. But there are other cones too. There are the two-dimensional cones. I guess here these are sigma 5, 6, 7, 8. I mean, numbered very uncarefully in the opposite way, but that doesn't matter. So, and sigma 9 is just the origin. So there are 9 cones in the span, and it is visibly closed under taking intersections and taking faces. So now, how do you form these U sigmas? Just let's do an example on one of these, such as U sigma 4. Okay, we need to find sigma 4 dual intersectional, which by definition is all the vectors in the dual lattice which pair non-negatively with 1, 0. So that would be the right half space. It's the closed right half space. And intersection with M just tells you that you should take the integer points. So each of those integer points corresponds to a monomial. Since 1, 0 is there, you have X in the algebra. Since 0, 1 and 0, minus 1 are there, you have Y and Y inverse also. And it's easy to check that these are the generators. So anything else can be written in terms of these. Now, the spectrum of this is isomorphic abstractly to C cross C star, essentially because this X factor gives you spec Cx, which is C, and Y inverse, that gives you Laurent polynomials, so that gives you C star. Now, in a similar way, you could do, let's do a neighboring ray, like maybe slightly non-trivial looking one, sigma 3. This is 3, minus 1. Then you would have U sub sigma 3. You do the same thing. This time you're, this is a straight line here. So the sigma 3 check is another half space, slightly bent. Now you might have to be slightly careful about picking generators and make sure that your generators are generators. So in particular, you could choose here xy cube and the y inverse. Well, if you look at the two vectors, the determinants or the area of that parallelogram is 1, so that's why you don't miss any points inside. But you still have to include x inverse. I mean, if you do xy cube, you also have to include x inverse y to the minus 3, because taking one generator on one side of 0 on that line wouldn't give you the negative automatically. You have to put them separately. But again, abstractly, this is the spectrum of this algebra is isomorphic to C cross C star because of similar reasons. I mean, here your Y inverse does give you a factor of C, and the other pair gives you the C star factor. Maybe it's important that these identifications are, I mean, in a way, not canonical. So this, we'll see this a little bit better in gluing because, you know, okay, so how are they glued? Well, there, in the surface case, there's a natural candidate to glue these, the big torus. I mean, that's the dual of sigma 9. So sigma 9 was the origin. So the dual of it is anything which, I didn't draw it here, but it's anything which pairs non-negatively with 0, that means everything. So if you have the full MR, then the integer points are M, and they are generated by, I mean, the monomials are generated by X inverse, Y, and Y inverse. And of course, the spectrum of this algebra is the full torus. So you have 2 copies of C cross C star glued over C star cross C star. So, I mean, you don't have to, I mean, the beauty of this thing is, I guess, so you don't have to worry about the gluing. It's given for you by the fan. Yeah, we have natural inclusions, U sigma 9 to U sigma 4 and U sigma 3, and you glue them to get their union. And you do this for all cones in the fan in order to get all of X. Maybe one small exercise, if this is the first time you are coming across toric geometry, find U sigma 7 explicitly. This U sigma 7 is this one between them, between sigma 3 and sigma 4. Find U sigma 7 and show that it is of the form U sigma 3 union U sigma 4 plus one extra point. Okay, now I want to make some remarks about toric geometry. First of all, the surface is complete, which in this setup means projective, if and only if the support of the fan is all of NR. The second comment is, okay, let's number the one-dimensional cones of the fan in counterclockwise, let's say. And suppose these are generated by primitive vectors v1 up to vk. Then checking smoothness, it turns out to be very easy. You should just check that. I think it's enough to write +1 because I ordered them. The X is smooth if and only if determinant of the matrix with columns vi +1 is equal to +1 for all I. Well, you take them cyclically, so I should be taken modulo K. If it is not 1, and that means there are singularities, there are some torus fixed points which are singularities, and it is possible to resolve them by toric blowups. Okay, another comment, as we saw several times before in this workshop, so each one-dimensional cone corresponds to a divisor which is isomorphic to P1 on X, and these divisors are T invariant, but not T fixed. So, I mean, they intersect at T fixed points, but the remainder points are moved by T within that divisor. So, well, one easy way to see is, okay, let's say tau is the one-dimensional cone that we're interested in. Look at the two neighboring two-dimensional cones, sigma 1 and sigma 2. Two neighboring one-dimensional cones. So sigma 1 and sigma 2 should be those red ones there. Okay, so you sigma 1, if you take away you tau from it, sorry, should it be the two-dimensional, or I guess it should be the two-dimensional one, I'm sorry. So sigma 1 and sigma 2 are the two-dimensional cones neighboring tau. So if you look at U sigma 1, U sigma 2, at least in the smooth case, you would find that they're copies of C cross C, and U of tau would be a copy of C cross C star. So if you take the difference, that's like C cross a point, so it's a copy of C. So these two copies of C glue together nicely to give you a P1. Okay, so consequently, if you do this for all one-dimensional rays, you get a chain of T invariant divisors, and their meeting points are T fixed. So this is the typical picture that we see. For each of these, you have a divisor. They just meet in a chain, and the intersection points are T fixed points. Okay, so I think I told this fifth remark already. So a T fixed point corresponds to a two-dimensional cone in a similar way. And suppose, okay, it's smooth for now. You can do a toric blowup, and that toric blowup would correspond to something in the some refinement of the fan. So you subdivide the relevant cone by inserting the sum of the primitive generators of the bounding rays. So suppose, I mean, this is the picture. So you have sigma, a two-dimensional cone bounded by tau 1 and tau 2. You insert a vector. Well, I didn't specify the primitive vectors in this picture, but you find the primitive vectors and you find their sum and just put one-dimensional cone. Of course, you also increase the number of two-dimensional cones by 1 in order to do that. This corresponds to a blowup. Another comment is SL2Z equivalence of fans give rise to T equivariant isomorphisms. So well, you could try to classify smooth toric surfaces. Well, there's the issue of blowups. You can blow up any number of times you want. So let's assume that there are no such -1 curves on the surface. So the surface is minimal. So then it turns out that it's actually an easy proof that every smooth minimal complete toric surface is one of the surfaces below. It's either P2, that's the leftmost picture, P1 cross P1, or here's a proof surface for some A greater than or equal to 2. The reason for not including 1, I suppose, is that has a -1 curve. Okay, now something about intersection numbers, and this was mentioned and used in Travis Mandel's talk. So let me give some more details about that. So, well, the toric divisors form a chain, so it's kind of clear how different such divisors intersect. So di intersect dj is 1, I mean the intersection number is 1 if you just get the next one, and 0 if they are far away, like j minus I is at least 2. So what about self-intersections? Now, something which is important for this and other reasons is the following relation. So for any m in m, let chi m denote the corresponding character. Now, the character is, first of all, a function from c star squared to c star, but you could extend it to x as a meromorphic function. So it would have zeros and poles, and then you could ask, what is its divisor? So then its divisor is given by the following formula. Okay, so find the primitive generators of the rays, defining the divisors, the i's. Then divisor of chi m is sum over m paired with vi, so you get some integers here, times di. Now, let's see this on the example that we talked about. Let's pick something simple like m equals 1, 0 on the M lattice. On the right side, you see the M lattice, which contains the rays of the fan. So let's look at what happens on V4 and V3. Well, the pairing of 1, 0 with 1, 0 is 1, so you expect to get D4 from here. But 1, 0 and 3 minus 1 is 3, so you should get 3 times D3. So I think it's instructive to also look at these algebras and see it there. U sigma 4 is spec of CXYY inverse. So the divisor D4 is just x equals 0. So I mean, and x equals 0 is its equation. So you get it with a factor 1. Now the other one is requires thinking for another moment. So this time it's the spec of y inverse xy cube and x inverse y minus 3. Now x is not immediately visible, but if you rename your generators y inverse and xy cube as a and b, then x is equal to a cube times b. So div x is actually, well, b is invertible in this ring, so that doesn't count, but a equals 0 is the divisor, d7. So did I write d7? It should be 3, I think. So the 7 should be 3, I'm sorry. So therefore, if you set x equal to 0, you get 3 times what you want. So the divisor of this meromorphic function is d4 plus 3 times d3 plus other things coming from the other one-dimensional rays. Okay, now once we have this relation, one immediately realizes that this div chi m must have 0 intersection number with any dj, because since it comes from a meromorphic function, this divisor is linearly equivalent to 0. And that means if you intersect that div chi n with any dj, you should get 0. Now, this relation should hold for every m in M, and this implies that these intersection numbers, di times dj times vi, the primitive vectors added over 1 to k, must be 0 as a vector. Now, this is a vector relation. And noting that dj's form a chain, dj intersects only 3 things: the one before it, the one after it, and exactly dj. So that gives this relation vj minus 1 plus dj square vj plus vj plus 1 equals 0 for every j. And since you already know the v's, from here you can deduce what the self-intersections should be. So this relation already appeared in Travis Mendel's talk. Okay, let's see this again on this example with these 4 rays. Okay, the primitive generators are 1, 0, 0, 1, minus 1, 0, and 3, minus 1. These correspond to these 4 divisors, d1, d2, d3, and d4. Well, for example, if you want to find d2 squared, well, you should look at sigma 1 plus sigma 3, which is 0. So that's 0 times 0, 1. Therefore, d2 should have self-intersection 0. Whereas for d3, you add up 0, 1, and 3 minus 1. That's 3, 0, which is 3, 0, which is 3 minus 3 times minus 1, 0. So d3 squared should be 3. And the other numbers are 0 and minus 3. So these are the self-intersections in this picture. Let's also do a fact check with maybe a single blow-up on P2, where we should get something familiar. So here is a blow-up of P2 at a single point. So if you remove sigma 2 from here, it's the ordinary picture for P2. And if you insert sigma 2, that's the blow-up at one t fixed point. So if you invoke the previous relation, you see that, okay, so let's look at d2. 0, 1 plus 1, 0 is 1, 1, which is the same as 1, 1. So to get a sum of 0, you must have d2 squared equals minus 1, which is, of course, exactly what we expect. And likewise, d3 squared and d1 squared are 0 because, you know, this 1, 1 and minus 1 minus 1 are now aligned. So, I mean, they add up to 0, leaving 0 for d3 and d1 squared, which is also in accordance with the fact that in P2, if you take the 2 lines, which have self-intersection 1, obviously, and do a blow-up, the blow-up decreases their self-intersections by 1 each. Okay. Now, let's come back to log-Calabi-Yau varieties, toric models, and cluster varieties in dimension 2, which are, I mean, we saw that they're more or less the same thing in a sense. So I'll just confine to the dimension 2 throughout for simplicity. So suppose U is a log CY surface with maximal boundary. That recall that this means it has some compactification xt, such that the canonical class of x plus d is 0, and d is normal crossing and has at least one singular point. The other way to think about that was there exists a holomorphic 2 form omega on x, such that omega is nowhere 0 on u and has simple poles along d. Okay, so we saw before that these surfaces are exactly those surfaces which admit a toric model. So let's recall what that meant. So we use a log CY surface if and only if, I mean, that was statement of that proposition. So use a log CY surface if and only if it admits some compactification xt, such that there's a toric surface x bar d bar and a birational morphism from x bar down to x, which is a composition of non-toric blowups. Now, these should be the proper transform of the bar. I hesitated about this in my last talk, but this was clarified in later talks. So the picture is something like this. So the green ones are the toric boundary of X bar, D bar, and then you do some non-toric blowups, and you take strict transform of D bar so that the major part of these red thing, except the point of intersection with the green, is included in U, in the new U. Now, I think it's also kind of beneficial to think about this in terms of the canonical class and the holomorphic form. So one general remark is for a general formula for a blow-up, I mean, the canonical class of X hat, let's do a blow-up at a non-singular point of the surface, it will be the pullback of canonical class downstairs plus the exceptional divisor. Now let's think maybe about the case of a single non-toric blowup, well, where P is located at a non-toric point on the boundary. That means, remember, this boundary is T invariant but not T fixed, right? So the T fixed points are on the other intersections. So P is not one of those points. P is somewhere else. So it's moved by T along that irreducible component. Well, if you blow that up, you get some EP. Well, if you do the canonical class computation, well, you should take the total transform of Kx bar, then add EP. Well, the point is that this D bar already passes through P and exactly once. So it will give you minus D bar minus EP. But then you add EP, therefore you get minus D bar, so that's why it works. In a sense, the zero and pole of omega cancel along EP minus. I mean, this pullback tries to produce a zero along that exceptional component, but at P, omega already has a simple pole, so these two effects cancel. I guess this is the main reason why we can modify these Loyang interiors by this process. Now, something important, which was also described in detail in Pierre's talk before this one, is that a given Loyang interior typically has many different toric models. Now, the point is each of these F's above loses information on you, so it contracts some EPs. Right. So, and the idea then is to build U as a manifold whose charts are these maps from U to various tori. So use all possible, maybe non-toric blow-up pictures of the same U and try to rewrite U as a manifold in that manner. And that leads to the notion of cluster varieties in the setup. So,
you mean like F is a birational map?
Well, first of all, F is a regular map, but it is birational. So its inverse doesn't exist, but it is birational. But first of all, it is regular.
T should go into U.
Sorry?
T should go into U.
No, the regular direction is from U to T. No, wait, so something I said is not correct here. So,
in each...
Yeah, so yes, I mean, EP doesn't go anywhere, sorry. Yeah, this is technically wrong. So, F is from U minus certain EPs to T, that's right. But I guess just, yeah, what I said here is not correct. So it doesn't, yeah, T and T goes, you are right. So this doesn't work on all of you, but the point is each point in U does have a neighborhood where it is mapped to some other T. So, I mean, the possible T's cover U, maybe except for codimension 2, I suppose. So, yeah, so this takes you to this setup of cluster varieties, which was described before. So you have various copies of C star square, and the transition functions are mutations or their compositions. And different toric models of U or combinatorially correspond to different choices of seeds. And you go from one seed to the other by mutation or a composition of mutations. Now, okay, something about this U-trop C. Yeah, trying to understand that. So one definition is, okay, one possible definition is let U be some log CY surface with maximal boundary. Look at all pairs F, K, where F is a boundary divisor in some log CY compactification XT, so it's part of the boundary divisor, not necessarily the full thing. And K is a non-negative integer. So, yeah, we'll look at all such pairs. Now, the motivation is, I guess, this is a globalization. I guess this is more or less the content of this Goncharo conjecture. This is a globalization of the notion of non-trivial one-parameter subgroups of a torus T. So, well, for a single torus T, so T, the non-trivial one-parameter subgroups is the co-character lattice, so it is N, right? So, but now you want to somehow do this for all the torus charts and put them together. So, well, if you want a non-trivial one-parameter subgroup, I guess you have to take away 0, so it's going to be, strictly speaking, Z2 minus 0, 0, and then yeah, so what's the relation with the divisors F and K described above? So each point in N, as in the toric picture, generates a one-dimensional ray, but then you have the issue of taking a primitive generator of that ray or some multiple. That's why you have K in the previous definition. And then, yeah, this issue about this integral affine structure is that you have one copy of N minus 0 for each cluster chart, but then, you know, moving from one to the other would have to somehow identify these, and that would be by an element of SL2Z, giving the integral affine structure. Yeah, I didn't write it here, but it was written in previous talks. So, well, the mutations tell you how to go from one torus to the other by a simple move, and like chasing that gives you how mutations should change one seed to another, essentially telling you how these Ni minus zeros are identified. Okay, so I wanted to say something about relation to other viewpoints of tropicalization. So I think this is related to a question Umut asked in the last talk and a discussion after that. So I'm not sure about this, but I think this is supposed to be true in some sense. So, well, tropicalization occurs in other contexts in geometry. So maybe the most well-known one, take some one-parameter family of complex algebraic hypersurfaces in some C star to the power n. Now the second C star is just the T coordinates. Okay, Now, one could apply the log map in order to obtain amoebas of these VTs for each T. So then you would have some picture like that. So you have a base like C star, for which T is a coordinate, and over each point you have log of your hypersurface, which really looks like some kind of amoeba. So these are like amoebas as in Gelfand, Kaplanov, Zielinski. So how you find them is you honestly apply log absolute map to each coordinates of the points of your variety, and that gives you down such shapes. Well, a typical thing to do is to take the so-called large complex limits. So what happens to this family when T tends to infinity? And you do get tropical hypersurfaces in this manner. Now, the relation to the U trop above seems to be via the second factor, C star. So, so choosing T is implicitly, actually, I'm choosing this one parameter family is implicitly choosing a one parameter subgroup of C star. But you could do this for other bases. So if you take a larger base T, C star to the power n, then the choice of one parameter subgroups then would be given by n, essentially, which is U trop of T. And I guess you could attempt to do this for cluster variety base instead of torus space. You could try to glue these bases together, and that's, I think, what that would give you. Okay, now two side remarks, one of which I wrote, the other which I didn't write. So one thing which I think is relevant, but I cannot figure out exactly how, is for VT as in the above picture, this amoeba picture, one can also construct the so-called co-amoeba fibration. So this time you apply not the log map, but the arg map to the coordinates. This amoeba, co-amoeba pair of fibrations gives Lagrangian fibrations essentially because they are real and imaginary parts of some other holomorphic coordinate, which is holomorphic log. And that's a very useful fact for many applications of amoebas. The second comment is if one tries to instead start from a single V without specifying any specific family of degenerations, but rather try to be greedy, like take all possible degenerations of this abstract variety in the sense and try to find a universal object somehow, then that leads to this rigid algebraic geometric objects such as Berkovich space or things like that. So there's a theorem saying that the limit of all possible tropicalizations is the Berkovich space of that variety. So I think we'll hear some things about non-Archimedean stuff in the conference. So, but I don't know if it's related to this. But yeah, I mean, the way I would think about the Tate curve or something like that would be trying to take all possible tropicalizations of that abstract variety without really confining yourself to a single base. Okay, now at the end, I want to do maybe a very concrete example, which I could maybe a little bit understand. So, and this was already mentioned in Travis Mendel's talk and Pierre Blousseau's talk. So there's a cubic surface in P3, but instead of mutations, I'll try to see different seeds globally somehow. So let's start from P2 as a toric model, which is the usual way, like 3 vectors adding up to 0. And you have 3 lines, essentially, 3 divisors, D1, D2, and D3, all with self-intersection +1. Well, the way to get a cubic surface from here, as explained before in other talks, was to take 2 non-toric blowups along each DI. So that would in total give you 6 points. Okay. Now, one additional thing which we want to assume is that these 6 points for those blow-ups are not on a single conic. So classically, through any 5 points, no 3 of which are on a single line, there is a uniquely reducible conic, but if you have 2 points on one line, 2 on another, and 2 on another, it's plausible that your conic intersects all 6, right? So, because the conic times the line, it could very well have 2 points, but that would be a special configuration. We don't want that. So we want these 6 points to be general in that sense. Now, okay, so take such 6 points and blow those up. Well, the self-intersections of D1, D2, and D3 were +1 when you began. So after 2 blow-ups, they will be reduced to -1. And of course, so the self-intersections of the exceptional divisors will also be -1. Now, this will give a smooth cubic surface in P3. This is very classical, and there are many ways to prove that by equations or otherwise. Okay, then this Lorentz interior here is this cubic surface S minus this triangle of lines D1 union D2 union D3. Now, a very classical fact again is that due to back to Cayley, I suppose. So there are 27 lines on any smooth cubic surface. So smooth complex cubic surface. So if you remove these 3 green lines, you'll have 24 on U. Right. So, well, one has to be a little bit careful about whether a rational curve is actually a line in P3 or not, but that can be easily checked by some classical geometry again. So these, after these blow-ups, these 3 green lines and 6 exceptional divisors are actually 9 lines, but there are 15 more. So the other 15 are, first of all, strict transforms of lines through these PIQJ, PIRJ, QIRJ. So there are 2 points on each line. Take 1 point on one green line, 1 point on another. We'll join them. That's a line on P2. Its strict transform is also a line. So in this way, you can create 12 more lines because you have 2 on one line, 2 on each. So there are 4 pairs for 2 lines, and you have 3 of them, so there are a total of 12. So at the moment, this accounts for 12 plus 6 plus 3. So this is 21 lines. So we need 6 more, and those 6 are coming from conics. So if you select 5 out of those 6 points, missing 1, and that's the reason, more or less, that these 6 shouldn't be on a conic. Otherwise, you wouldn't get a smooth cubic. There are 6 ways to leave out 1 point. So you have 6 conics through 5 of those points. And you can check by intersecting by a hyperplane in P3 that when you, after this blow up, the strict transform of this conic intersects the hyperplane in P3 at 1 point and not 2. So that becomes a line. So this is the rest of the lines, and we have all 27. Now the upshot is, okay, we can view things backwards, right? Coming from U down to this toric model, we have to blow down a sextuple of disjoint lines, right? Disjoint -1 curves. But the point is, this cubic surface has lots of symmetries. More precisely, the configuration of lines, if you think of it as an abstract configuration, has a large group of symmetries. It's something of the order, I think I wrote it here, 51,840. So it's a very large finite group. Well, even if you remove the green lines which are not on U, there's still lots of symmetries remaining. So it's, I think, intuitive at this point that this sextuple of disjoint lines shouldn't be unique. You should be able to find other sextuples to blow down. And by the way, blowing down is easy matter because we know Castelnuovo's theorem. If you have a -1 curve on a smooth surface, you can blow it down and still get a smooth thing. So all then to find different seeds, all that we have to do is to find other sextuples which are disjoint, right? So I mean, and that's if we go back to the original picture, the 6 lines that we find after blowing up those 6 points were disjoint, right? They're exceptional curves of points which are far away. Now, so therefore, viewed backwards, the 6 sextuples of lines on U that we want to blow down, again, should be disjoint. Okay, and I think, show you that there are many such sextuples. So, for example, form a triangle first by taking one point P on one line, another point Q on another line, and R on the third line. Okay, so just join these 3 points, you'll have a red triangle. Now, these lines, of course, do intersect in P2, but if you blow these 3 points up, which you should do in order to get U, then up in U, they will not intersect. They look at different directions, right? So those will be disjoint. Now, you need 3 other things to be able to finish the sextuple, and you can find these by looking at conics. It's awfully difficult to draw the conics. The first reason, I guess, the picture being real rather than complex, but we can think of it a little bit abstractly. So you fix the 3 points, and you have 3 other points that the conics could avoid, right? Remember, each conic misses just one of these 6 points. So there are 3 other conics passing through the 3 chosen points and passing through 2 of the non-chosen points in our list. And it's, again, an easy matter to check that those conics will not be tangent to each other or not be tangent to the red lines, which implies that when you blow these points up, the visible intersections on this picture will all disappear in U. So you'll have a disjoint sextuple of lines in U, and that will give you another seed, right? So this will give you a seed different from the one that you started with. Now, I think it's fun to try to count the number of seeds that you can get in this way. Well, we can get, well, you have to choose P as one of the 2 points on one line, Q as one of the 2 points, and R as one of the 2 points. So you'll get at least 8 different seeds in this way. And with your original one, this produces at least 9 different seeds globally, where, you know, it's the same U, but you can project in different ways and get different toric models, essentially. I don't know if these are all. I mean, so I didn't do any check like that. I don't know the answer. And I cannot yet decipher some other notations. So I'd be happy if someone can tell me. So this is all I wanted to tell, basically.
Okay, let's So any question? I think it might be okay to ask more general questions too than what was in the lecture. Yes, as long as they're simple. Something about toric varieties, maybe. Well,
I didn't understand the part about the intersection number being 0. At very first, at third variety.
You mean div of chi m, or?
Yes.
Ah, okay. Yeah, sure. I could go back there. So let's see, where was that? Yeah, right here. yeah, I guess the point is chi-m is a meromorphic function. So then by definition, it means that its divisor is linearly equivalent to 0. And this major yoga of intersection theory is, I guess, it is well defined up to linear equivalence. Actually, some other equivalences as well, but as a first thing, it is well defined up to linear equivalence. So if something is linearly equivalent to 0, it should intersect any other divisor with 0 intersection number. Maybe more geometric way of thinking is that if it is the 0 and pole locus of a function, you could kind of move it around and you know, cancel the 0 and pole. I mean, this is not rigorous, but this is how maybe the classical algebraic geometers thought about it. So you could deform and you bring the 0 and infinity together to cancel the plus and minus part. That's how they thought about Bezout's theorem and things like that. But you know, you can make this precise, and you know, intersection theory works nicely, and divisor of any meromorphic function is intersecting trivial with anything else.
Other questions? Okay. Online questions? Is there any? I don't know how many people are online. Okay, well, let's thank Özgür Hoca again.
Thank you.